Hey guys, my name is Akshay and I'm going to be presenting my findings for Lab 3. The purpose of the lab was to look at distance dependence of a magnetic field produced by a bar magnet and compare our experimental data to the computational model that we made. In the actual experiment, the first step that we did was to identify the location of the magnetometer sensor on our smartphones. We then moved the magnet closer to the sensor to find distances for various Tesla values. And finally, the last part of the experiment was to find the perpendicular distance, which would give a net magnetic field of 100 mu teslas, and we took data when the sensor was 45 degrees from the magnet. So here are the physics principles. The first principle is that moving particles or magnetic objects produce magnetic fields which can be observed. We're going to have bar magnets create a magnetic field, and the direction of the magnetic field points away from the North Pole and towards the South Pole. Another principle is that Earth has its own magnetic field, which varies at different latitudes and longitudes. And finally, we have the superposition principle, which here means that the net magnetic field is the sum of the magnetic field produced by the magnet and the magnetic field produced by the Earth, and we can ignore the effects of the Earth when we place our phone east to west. Here are my results and observations. I found the magnetometer sensor had an x component magnitude of about 18 mu teslas even when far from the magnet. As the magnet moved closer, the x component increased. When I graphed the net magnetic field versus the distance, I found I had the equation y equals negative 3.2x minus 15, where natural log of k is the y-intercept and n is the slope. This is a little bit off from our expected n and k values. The expected n value is negative 3 and the expected k value is negative 16.11. Here's a graph illustrating what I just said. We're going to have a slope of negative 3.2 and we're going to have a y-intercept of negative 15 when we graph distance versus the magnitude of the magnetic field. Using this data, we can calculate the magnetic moment. To do so, we're going to use the equation B bar equals U0 divided by 4 pi times 2 mu over r cubed, where mu is the magnetic moment. From the graph that I just showed, natural log of k was negative 15, meaning that k is going to be 3.06 times 10 to the negative 7. I found the mu values for the 5 different r values that we were working with. For r of 20 I had 0.734, for r of 70 I had mu of 0.6, etc. And I got my average mu value was about 0.83. The magnetic moment that we calculated is going to come really handy for the computational model. So here is my computational model. The computational model helps to visualize the magnetic field around the magnet and removes the need for us to do these calculations. We've created a function which calculated the magnitude of the magnetic field at some distance from the magnet, and this equation, as you can see here, uses mu, and mu is a dipole moment, which is why we calculated it earlier. Our computational model also looked at distance dependency for 4 charges perpendicular to the x-axis and 2 charges parallel to the x-axis, and we could visually see the direction of the charges. We also computed the magnitude of the magnetic field 45 degrees from the axis, and we compared the magnitude of the magnetic field from the model to the one that we determined experimentally. So here's a picture of my computational model. Relating this back to the physics principles, you can see how the magnetic field produced by the bar magnet is going to point away from the North Pole and towards the South Pole. Here, that means that the North Pole is going to be on the right end of the magnet and the South Pole is going to be on the left end of the magnet. So some additional questions to think about are, what if we hadn't accounted for a magnetic north? In this case, the magnetic field components of the bar magnet probably couldn't have been found, since Earth's magnetic field would also have contributed to the net electric field, and this is because of superposition principle. And if 2 bar magnets were stuck end to end, then the magnitude of the magnetic field would be double of what was the case for this lab, and I would expect the distances R to be half. So to wrap up, the goal of the lab was to better understand distance dependency for bar magnets and be able to visualize the magnetic field through a computational model. We can compare our computational models with the experimental data to get a sense of how good our data really is. The computational model for the 45 degrees was 1.81 times 10 to the negative 5, 5.43 times 10 to the negative 5, 0. The actual results were here, as you can see. So overall, the data that I got could have been better. Sources of error could be possibly bumping the phone, not resetting the app, etc. When you compare the magnitude of the magnetic field that I got from the computational model and my actual data, there was about a 60% error, so there is some room for improvement there. Alright, so that is the end of my presentation. Thank you guys for watching.